which is Felix Küng, and he's going to talk about twisted Hodge diamonds give rise to non-Fourier-Mukai functors.
Okay, so thank you very much that I can talk here. It's an awesome conference so far, and also please interrupt me if I'm going too fast or forget something, or if you have any questions. So there are a few things that I might be skimming over, but I can always go into detail. And so this is part of my PhD thesis, and hopefully soon also a paper. It's essentially just proofs always need a little bit more of polishing, but the work is done, and all of these things I just want, I've got the proofs and everything works out, just the nice writing down. So what we will talk today about is about how we can construct non-Fourier-Mukai functors, and that we can use twisted Hodge diamonds to do that. So we will start out by talking about some preliminaries and the story so far, because that has been quite an important subject for a few years. And then we will talk about what we actually do. So first, how you actually can construct non-Fourier-Mukai functors, and then how twisted Hodge diamonds actually get into the picture. Because there are a few things going on. Like, it is already hard to construct non-Fourier-Mukai functors, but the bigger problem is actually to also verify that they actually are not Fourier-Mukai. So let's first of all fix some notation. Throughout this talk, K will always be a field of characteristic 0, because actually if you are not in characteristic 0, it's not that hard to get non-Fourier-Mukai functors. However, in characteristic 0, it's a really big thing. Then all of our schemes will be over K. We will denote by d of x for the derived category of a K-linear category X. So just think about X as a fancier ring. And we will denote by dbx the boundary derived category of a scheme. All of our schemes will be smooth and projective, so that we can really say, in these cases, even in these cases, we find non-Fourier-Mukai functors. And I didn't want to drag along a lot of R's and L's, so we will always consider derived functors. So I hope this is okay for everyone. And so if we have two schemes, and we have a functor between the bounded derived category of these schemes, then we call a functor Fourier-Mukai. If we have in the product, if we have in the derived category of the product an object such that our f is actually the same as pulling back along one projection, tensoring in the product, and then pushing down again. Now, the really cool part about this is actually that nearly all of the functors, well, I actually think all of the functors you know are actually Fourier-Mukai. So for example, direct images, pullbacks are Fourier-Mukai, shifts are Fourier-Mukai, tensor products are Fourier-Mukai, and essentially all the functors that one usually encounters in algebraic geometry are Fourier-Mukai. And for a long time, it was actually even conjectured that all of the functors are Fourier-Mukai, because one can go even further and prove that if the functor f arises actually as a functor of DG enhancements, where, for example, you just take the canonical DG enhancement of your bounded derived category, then it is already Fourier-Mukai, because on the DG level, every functor is Fourier-Mukai. Was there a question somewhere? Okay, then I go on. So it seems like a lot of the functors that we actually see should be Fourier-Mukai. And it gets even worse, because Orloff proved a very famous theorem where it proved that if you have smooth projective schemes and a functor between the bounded derived categories, then you immediately get that as soon as it's fully faithful, that you already have that it's Fourier-Mukai. And it gets even worse, because one can actually prove that in these settings, it suffices to be full, because as soon as your functor is full, it actually becomes already faithful and you're done. And so this makes it, after that, it was actually believed that, wait, maybe all of the functors are actually Fourier-Mukai. However, a few years ago, my advisor, Alicia Lizardo, Michel Vandenberg, and Amnon Niemann actually constructed a non-Fourier-Mukai functor by taking the embedding of the three-dimensional quadric into the four-dimensional projective space, and then deforming this quadric in a non-geometric way and then pushing by deforming it in a non-geometric way and pushing it down into the projective space again. And this functor can actually be proven to be non-Fourier-Mukai by using A-infinity abstractions and using A-infinity abstractions. Now, there are a few things that go well here in order for this to work. So one thing that is lucky here is that a quadric admits an exceptional sequence. So you always have a tilting bundle, which helps you control set abstractions. Then you have that in the deformation, you use Hochschild cohomology. And if you take the three-dimensional quadrics, then you have that 3 plus 3 is the same as n plus 3, where n is the dimension. And so that's also helpful. And we'll later see why that's precisely why that's an issue. Now, later, Alicia Risado and Michel van den Berg and Theo Retschelders, I know I butchered that name, but I'm very sorry about that. But they realized that the algebraic, the category you deform dbx into is actually still a geometric category, which means that there is somewhere out there a huge scheme that you can embed into fully faithfully. And by that, you can actually, again, get that these functors are non-Fourier-Mukai, because you can, if you have this big scheme Y and a fully faithful embedding that is very well behaved, you can actually push forward again these abstractions and control them. However, the big issue here is, well, we get a lot of Fourier-Mukai functors, but there is no way of controlling it. This Y exists due to an existence result of Orlov, and by the usual thing about existence results, it tends to be very big and ill-behaved. So there is no real way of properly controlling these functors, and that's where my work comes in, because I wanted to mimic the previous construction, but improve it so that we can go in higher dimensions and have more degrees. And so that's actually my result. If we take a smooth odd-dimensional degree D hypersurface, then there is an exact functor that is non-Fourier-Mukai. Now, the odd dimension is something really intriguing, but this is so I proved this, but let's first talk about how you actually construct non-Fourier-Mukai functors. So how does one go about that? Well, first of all, I said that you actually take your derived category and deform it in a non-geometric way. Now, in order to do that, we somehow need to get out of the geometric world. And for that, Wendy Loewen and van den Berg constructed functors. I think that's by now something very generally known. Functors that embed your derived, that construct to a scheme, a k-linear category, and embed fully faithfully your bounded derived category of your scheme into your derived category of your modules. So that way we can pass from the geometric world into the algebraic world. And what is even cooler is that there is also a second functor that essentially does the same, but it maps the direct image of the diagonal embedding into the derived category of bimodules. And the cool part about that is that way we can compare the Hochschild cohomologies and actually get that the embedding is compatible with the Hochschild cohomology of our space and of sheaves on it, which will later be important because that's essentially what you deform along, because that's what you do with Hochschild cohomology. You deform stuff. Now, after passing to modules, what we do is we deform. So if we have a k-linear category, you can construct and you have a non-vanishing, or it also can be vanishing, but it's only interesting if it's non-vanishing. You can construct a non-vanishing Hochschild cohomology class. Then you can construct an A-infinity category over your field, where you just essentially take the original category and just plug in a higher action that's literally your eta. So you just take a category and say, I've got this eta there in Hochschild cohomology. So I just add it and get a new category. And if you forget about this new eta, you get your original category, of course. And so that's why it comes with a natural projection pi from x eta to x. So you you just add in a new action. Now, as this is essentially, as this project, this is essentially a non-trivial deformation because you can take your eta to be non-zero. This functor that gets induced by forgetting the action should not be in any way dg and by that Fourier-Mukai, and that's actually what you can do. So if you have an n-dimensional scheme and you have a bimodule, then you can deform you can take your x eta, you can construct it, and you actually get a functor from your derived category of your scheme into this derived category of an A infinity category. And this is right inverse to the projection, but due to that, it should not, in no way, there should be no way at all that this thing is actually dg. And that's essentially the idea. This L is a functor that is non-dg, and we will use that. So, but after that, we are now in the derived category of an A infinity category, which has no reason at all to have anything to do with any geometric thing. So what we then do is, if this eta that we deformed along is actually in the kernel of the push forward along your functor, you can get a diagram like that, which means that you can actually embed, because if you pass through the algebraic world, all your morphisms become functors the other way around. So if our embedding goes from x into Pn, then we can suddenly embed x eta into what corresponds to Pn. And so we can immediately go back into the geometric world. Now, the tricky part is that we need to have eta in the kernel of the push forward in Hochschild cohomology. And Hochschild cohomology is never the easiest thing to compute. However, so the complete construction is you take your bounded derived category, you make it into an algebraic category, you deform it and use this L, and then you go back to the geometric world. And that construction works in general for every m that's bigger than n+2 and every eta that's in the kernel of the push forward. Now, in order to prove that this is non-Fourier-Mukai, which is the really hard part, you use obstructions, infinity obstructions against lifting to equivariant structures. And the really cool part, if you chase through these numbers, is that the problem that arises here, if you want to prove that it's non-Fourier-Mukai, is that there might be new choices arising, and these obstructions are inductive. However, if you somehow can manage that the first obstruction doesn't vanish, then there are no choices and you are done. And what you need for that, if you chase through the numbers, is to pick your eta in the kernel of the of the push forward in H8 n+3. And so that means as soon as we can control this kernel in degree n+3, we should get a huge amount of non-Fourier-Mukai functors, or more precise, we should get for everything in here a non-Fourier-Mukai functor. And that's what I did. But so, of course, since we want to compute the kernel in Hochschild cohomology, what we first do is we try to compute Hochschild cohomology. And when you compute Hochschild cohomology, there's one nice thing you can sometimes use. That's the Hochschild-Rosenberg isomorphism. But in order to use that, you stumble upon these so-called p-twisted Hodge numbers. So essentially, you take your Hodge numbers and your definition of it, and just throw in a twist of p. And you can arrange that as a Hodge diamond. And so essentially, you just have a lot more Hodge diamonds, twisted Hodge diamonds, and they don't tend to be symmetric. Now, Brückmann did something very nice. So one can use these by the Hochschild-Rosenberg very nicely, isomorphism very nicely, to compute the Hochschild cohomology. Because if you just apply the Hochschild-Rosenberg isomorphism to the Hochschild cohomology, you get that it's a direct sum of precisely the spaces that of which dimension make your twisted Hodge diamond. So you can take your Hodge diamond and just look at your columns, and these are the HHIs. So this is the HH0, then you go up, this is the HHN, and this is the HH2N. So every column it becomes the dimension of your Hochschild cohomology. And after computing that, you are of course interested in how these Hodge diamonds, twisted Hodge diamonds actually look like. And then you get lucky because Brückmann actually computed in 1974 all those Hodge numbers for degree D hypersurfaces. And these twisted Hodge diamonds look in general like this. So you have everywhere 0 apart from the middle vertical diagonal, which is a Kronecker delta. So that only appears if our P is 0. Then we have the boundaries and we have a middle part. Now, if you compute this, it actually turns out that the red middle part disappears for the projective space, which kind of means that this red middle part can't come from a pullback from the projective space. So this should be the kernels of the push forward in Hochschild cohomology. And you can actually prove that, and that is what I did. So if you have an embedding of a smooth degree D hypersurface, and then you can compute that actually the kernel of the push forward along this embedding is precisely controlled by these middle parts. So every part here, these are the dimensions of the kernel of the push forward in Hochschild cohomology, except for here, because here the green and the red line collide. And so we just repair that by taking something a little bit different, but that essentially replaces the middle part there. And you can actually also think in this diamond about having a bottom part, an upper part, and a middle part, and here they collide. And you somehow need to extract that here it's only the middle part. But this means that we actually get complete control about the kernels of the push forward in Hochschild cohomology, which we can use to construct non-Fourier-Mukai functors. And so, for example, if we take the Hodge diamond, twisted Hodge diamond, 8 twisted Hodge diamond in X, where X is of smooth of degree 7, then we get that this, as I said before, we want HHN plus 3 to be an HHN plus 3. So we take this is n plus 1, n plus 2, n plus 3. And this number here is the dimension of the kernel there. And so we get 20,939 dimensional space of possible deformations that give us non-Fourier-Mukai functors. And so if we put that together, we can actually prove that if we have an embedding of a smooth odd dimensional degree D hypersurface, then we can construct an exact functor between the bounded derived category of X and the bounded derived category it's embedded in, such that is not Fourier-Mukai. And actually, okay, we have a big space here, but those might still theoretically be isomorphic. That is kind of hard work to really prove that they are not the same. However, we get for every number between D and n plus 5 halves D minus n, at least already some that are guaranteed different, and then we have still this big space. So this is what I was working on and what I'm currently writing down, and hopefully is out in a few months. And so I was faster than expected. I'm very sorry about that, but that means that I can say thank you for your attention, and please feel free to ask any questions, and here are the references.
Okay, so let's thank the speaker.